Today's topic is about making your own ChatGPT, and that is just to get you interested. We'll be covering mainly the basics of NLP and taking you to till making your own ChatGPT. So let's start. First of all, yeah, that's what I was saying. Where are you learning machine learning from? Well, you could be learning it from your university. You could be doing from online courses, from YouTube, from our workshops, articles, or you could be learning from memes, and that is perfectly fine. Because articles, workshops, they do definitely give you good insight. But memes and fun videos, fun applications of machine learning are what get you actually interested in it. So, first of all, let's start by demonstrating the models. So, Vishnu here would be demonstrating the models for you and how you can actually make your own ChatGPT.
Well, hello all of you. It's nice to see you all here. Let's just jump into the demonstration immediately. So today we'll be looking at a model called Alpaca, which was released recently by Facebook or Meta. Yeah. Now because pickup lines are funny, we'll be asking the model to generate a few pickup lines. How's that sound? So yeah, don't worry what these parameters mean. We'll be telling you all of them in the upcoming slides. So yeah, okay, there's an error there. I'll just try this on the place. We'll be looking at that also. Just try to generate this in the meantime. Okay. That's giving us an error. That's not in my control, so just ask it for. So yeah, we'll just be asking these. Yeah, sure. Here are some pickup lines you can use. You look like someone I used to know. You remind me of a song I like. You're funny, you know. Well, these are abysmal, but as we'll be seeing, model size is integral to the quality of the model's output. So yeah, we'll be going further. Now we'll be coming to the interesting part where you can code your own model. I'll just show you the Google Colab demo. So yeah, this here is Google Colab, where you can run your own models. You just search a bit. We'll be using a model from Hugging Face. If you don't know what Hugging Face is, it's a space where people put AI models up, which are fine-tuned or trained. So yeah, let's just go to the Hugging Face space. I'll just tell you how to use a model. Today we'll be using a model called Instruct GPT-J. So yeah, as you can see here, we got all the information about the model here. So all you have to do is just copy this, paste it in, and just run your Colab. So I've already loaded this up because it takes quite a while to load, and we'll be seeing what answers it gives. So yeah. So I've asked for the model's name and asked it for its favorite food and origins. So my name is Name apparently, and it loves to eat pizza. And because the model is a know-it-all, which starts going into details about pizza, its origins are Italians and such. Okay. Now because I don't know how the model seems to also deduce that we have exams coming up in 2 weeks, so it's giving us methods to reduce stress over here. So meditation, yoga, the usual. Okay. So later on I've asked it for the name of its favorite TV series and its favorite characters in the TV series. Its favorite TV series is Game of Thrones, apparently, very popular. Season 8 was a disaster. So yeah, it's giving us full details of what its favorite characters: Jon Snow, Brave and Noble Knight, such. There are some bonus models here. You can just go look up at the Colab. We'll be sharing these slides, so feel free to go look those models up too. Thank you. Now, Amit Kumar Makkad will be coming over to teach you the basics of NLP.
So hello everyone, I am Amit from third year CSE. So before going into the ChatGPT, let us look at some of the basic stuff. So for getting into the models like ChatGPT, for before getting into that, our model should able to understand human language. So NLP is the field of AI and computer science that deals with enabling machines to understand, interpret and generate human language. So there are many applications of NLP like in email filters. Email filters, you see email contents and they classify whether it goes into spam or not spam. And then smart assistants. I hope all of you have used smart assistant, right? So smart assistants are able to understand our human language and they do whatever tasks we assign to them. And then we have Google translators or language translators which knows both the languages and they are able to map one language into another. So now let us look at how they are able to do these things. So for making any model, we first have to set up its pipeline. So pipeline is just basically the workflow. To set up an NLP pipeline, there are three steps involved in it. The first step is text preprocessing, the second step is feature extraction, and the third step is modeling. We will look at each step one by one. So in text preprocessing, basically we remove some unnecessary things from our raw text data. Like in the clean step, we remove some punctuation marks or the special characters which does not add any meaning. And in normalize, we convert all our text into either lowercase or uppercase so that we can maintain consistency. So basically, we are trying to make our text into a structured format so that we can further analyze it. So in the upcoming slide, we are seeing some major steps from this part. Okay, the first one is tokenization. Tokenization is the breaking of the raw text into small chunks called tokens. These tokens help in understanding the context and developing the model for NLP. Like tokenization can be done in many ways. There are many types: word-based tokenization, character-based tokenization, and subword-based tokenization. The figure in the left side shows you the word-based tokenization in which we have a sentence, let's go to New York. So we will tokenize it into small tokens. Let's go to New York, and then other punctuation marks also there. After we tokenize, then we can remove our stop words. Stop words are the words in any language which does not add much meaning to the sentences, like is, for, the, are. We can ignore these words without sacrificing the meaning of sentences. Then another problem is that like some words are present in different tenses. So like we want our model to understand both the words as the same words in different tenses as the same thing. So for that problem we use stemming and lemmatization. Stemming is the process of removing suffixes from the words to get the root form, like change, changing, changes, change, changer. From that we remove the suffix e, ing, es, ed, er to get the root form chang. While in lemmatization, it involves mapping words to their base form using dictionary or knowledge of language morphology. In this change, changing, changes, change, changer will convert into word change. Change has a physical meaning, while the word chang does not have a meaning. So stemming is just removing the suffixes, while lemmatization is mapping the words to their base form. So that's why stemming is a very faster algorithm, while lemmatization is slower. Stemming is used in where when the meanings of the word do not carry, when the meaning of word is not useful, while lemmatization is used where meaning are very useful. Let's say in a Q&A application, lemmatization is used. Then we have byte pair encoding algorithm. It is a type of subword tokenization in which words are broken down into smaller subwords. It is an advanced algorithm. It is used in a lot of transformer models including GPT and GPT-2. It was originally a data compression algorithm, but we now use it in NLP to find the best representation of text using smallest number of tokens. So in this flowchart, the algorithm is there. Let's say we have a text space, and from that text space we take all unique words, and then we get count of each of them. Imagine there is a text space given here in which hug appears 10 times, bug appears 5 times, pun appears 7 times, bun appears 9 times, hugs appears 3 times. And then we can get all unique characters like H, U, G, P, N, B, S, and this all unique characters represent the vocabulary here. Then we have to pick a consecutive pair that has highest co-occurring count. Like from this statement, like we can take UG. In hug, UG appears consecutively 10 times, in pug 5 times, in pun 0 times, in bun 0 times, in hugs 3 times. So overall they are occurring 18 times. Let's say for UN, can anyone tell me how many times UN occurs? So in hug 0 times, in pug 0 times, in pun 7 times, in bun 9 times, in hug 0 times. So, so overall UN occurs 16 times and UG occurs 18 times. So we will pick UG as a token and add it to our vocabulary. So now our vocabulary changes to HUGPNDSUG. Then again we have to do the same thing in a loop. We have to pick the consecutive pair that has highest co-occurring count, and then we have to add it into our vocabulary. We will continue up to we reach a desired predefined size of vocabulary. When we reach a particular size, we can stop. So in that way we can make the subwords tokens. So these are the some steps of text pre-processing. Now we will move to feature extraction. So basically now we have a structured text so that we can do our analysis. But as of now also we cannot put it into the ML models because ML models require numerical text to work with. So now we have to extract features from our text data and then we use it to train our model. So there are many common techniques like bags of word, TF, IDF, word embedding. These are all used to generate vector from text data. So now the first one is bags of word. It is a very basic algorithm. Here text data is represented as the vector of word frequencies. We have, let's say, the 4 sentences: the red dog, cat eats dog eats food, red cat eats. So these are the sentences. So now we have to find some unique tokens from it. So the unique tokens are the, red, dog, cat eats food. Like the column here represent the unique tokens present in the all sentences. So now let's take in sentence the red dog. In this we have to map the word frequencies into their respective cell. In the red dog, the comes one time, so we will put 1 in this cell. Red also comes one time, dog also comes one time, cats comes 0 time, eats comes 0 times, foot comes 0 times. So in that way we get a vector 1 1 1 0 0 0, and for cat eats dog we get vector 0 0 1 1 1 0. So now we get a vector from our text data. Now we can use it in our ML model. But as I said earlier, it's a very basic algorithm. So it is used in like search queries when we have to find a particular word in a sentence. So the problem with the previous model is that many words which are repeated again and again are given more importance in final feature building. So we miss out the context of some less repeated words. So to avoid this problem, we use TF-IDF instead of word frequencies. TF-IDF measures the frequency of the word in a document and IDF measures the rarity of the term in the corpus. Corpus is basically the set of documents. So higher the TF-IDF score of a term in a document, the more important it is. This is because the term is both frequent in the document and it is rarer in the corpus. So this type of algorithm is used in the keyword extraction where we have to find some important keywords. So now we have word embedding. It is most widely used in the machine learning because word embedding, it solves the problem of the synonyms and antonyms. Like let's say we have a word and its synonyms occurs in that sentence. So we want our model to take both the synonym as the same thing. So word embedding provides vectors which have similar meaning, means the words with similar meaning have the same representation in word embedding. So there are two methods to get word embedding: word2vec and glove. Like first, word2vec works by training a neural network on a large corpus of text. The neural network learns to predict the context words or the target word based on the input text. The weight after training, the weights of the neural network are used as the word embeddings. Here it's a quite complex algorithm. I am not completely discussing it here, but you can appreciate its example. Like in the example, you can see the vectors are given. Like after word2vec, we get vectors king, queen, man, and woman. So if I do here king, woman and man are the vectors. So if I do vector addition of king and woman and then subtraction of man, so it will generate a vector which is very much similar to the vector queen. So it captures the semantic meaning in this up to this extent. Here also a similar example in which some words from Google News means word embedding of some words are plotted here. Like you can see here the all the words with the meaning of days like Saturday, tomorrow, Thursday are very much close to each other because they have very much similar representation. So the another algorithm is Glove. Glove works by constructing a co-occurrence matrix from a large corpus of text where each element of the matrix represents number of times a word appears in context of another word. Then the matrix is factorized using matrix factorization techniques to obtain low dense vectors. So the key difference between both of them is that Glove considers the relationship between all pairs of words, while word2vec takes the relationship between nearby words. So that's why word2vec is preferred for analogy completion tasks like the example which I showed you of king queen. And Glove is used for the tasks that require capturing syntactic relation, basically it's grammatical relationship between words, such as parts of speech tagging. So now you may think like words get a vector, dogs get a vector, everything gets a vector. But this is how ML works. I hope anyone having any doubt till now? No? So from now, my friend Parth will continue about the modeling part.
Thanks, Amit. So, hi, I'm Parth from third year CSC. So, now, as Amit said about text preprocessing and feature extraction, now we will move on to modeling. So, first of all, we will look into three models, three NLP models, RNN, LSTM, and transformers. So, we will look at them one by one. So, before we move on, let's see what is a neural network. How many of you here know what is a neural network? Okay, so some of us don't know what is a neural network. So I will just give a brief overview. So in a neural network, there are multiple layers. So here you can see first one is the input layer, so which takes on multiple inputs. Then we multiply it by a weight matrix to get the output. Then we multiply some when they apply some activation function and get the final output. Then ultimately we can use this neural network for different tasks like classification and others. So this was just a brief overview of neural network. So initially when you start learning machine learning, then you apply different models like linear and logistic regression, then decision tree, random forest and all. But ultimately then you move on to deep learning. So and you forget about all the models. So now we will look at what is a sequence to sequence model. So a sequence to sequence model basically takes a sequence as an input and gives a sequence as an output. So you can take an example of a translation exam. So in a translation, let's say you input an English sentence and you output you get a French sentence. So it is a sequence to sequence model. And here it is black box. So we don't know how exactly the translation is happening. So inside, what is inside the black box? Let's see now. So first of all, when you give the English sentence to the translation model, so first it passes to an encoder. So the encoder captures the meaning or the context of the sentence. Then after the meaning is captured by the encoder, then the output passes to the decoder. Then the decoder maps to the corresponding words of the vocabulary of the second language. For example, if you are talking about English to French, then the encoder will capture the meaning in English language, and then the decoder will see what are the corresponding words in French, and then it will give the French output. So now we will look at the first model, which is the recurrent neural network. So here there is a German to English example. So first the German sentence is "Komm bitte her." So initially the first word goes to the encoder RNN. So you can see here H1 goes X1 goes to the encoder RNN, then its output H1 then goes to the second encoder, and along with the second word. So one by one, first we pass on the first word to the RNN, then its output, and it takes the second word. So first comb goes to the RNN, then it is encoded. Then the second word bite is again goes to the RNN, and then the third word her goes to the RNN. So one by one we can see after the third encoder the whole sentence is encoded. So if you have any doubt till now, you can ask. Anyone has any doubt like how the encoding works? Yes.
That RNN is the same network or that three different?
Yes, RNN is the same, but there are multiple blocks of the same RNN. So in the first RNN, only the first word goes. Then afterwards, we get the output of the first word. Then along with the output of the first word, and then the next word. So they both go into the next RNN. So one by one, when we complete all the words, then we will have the encoding of the full sentence.
So here totally we have 6 networks, 3 encoders and 3 decoders.
Yes.
It's different.
Yes.
Same.
The architecture of the whole RNN is same. So like these 3 ping blocks, 3 encoder blocks are same, and then the 3 decoder blocks also are same, but only the inputs and outputs differ. Yes, it is series. See, it is sequential. So first you pass on the first word, then you get its output, and then you can see in the second encoder that H1 goes and X2. So what is H1? H1 is the encoding of H1, X1. So the encoding of the first word and the new word goes into the next encoder block. So you have to pass on the input sequentially. You can't pass it parallelly. So after the 3 words, you can see you get the output C of the encoder. Then it is passed on to the decoder. So inside the decoder, now the decoder will map the corresponding words in the output language, and it will give the output one by one. So the first decoder block gives the first output word, then the second gives the second output word, and so on. So ultimately you get the translation like please come here. So after passing through all the decoder blocks, you ultimately get your final output. So again you can see the animation once. So the German sentence "Komm bitte her" was translated to "please come here" in English using encoder and decoder. So anyone has any doubt in decoder? So now we will move on to the next slide. So now again the same problem. What are the problems with RNN? So the first problem is the input is taken sequentially. So there is no parallelization. Then the second problem is that once we give it a new input, like here the first sentence was passed. So in a paragraph there can be multiple sentences. So if you pass on the next sentence, the RNN forgets the previous sentence. But it should not happen, like it should remember the context. So for a long paragraph, the RNN will have difficulties in remembering the previous information. So that is one major problem with RNN. So to overcome that, we have a next model, which is known as LSTM. So what is LSTM? So LSTM stands for long short-term memory. So this is the LSTM cell, and it consists of different gates. So I will tell you about 3 main gates. So first is the input gate. So what does the input gate does? So it controls the access of the information to the cell. So it will monitor what information will go into the cell. Then there is the output gate. Then it will monitor again the access, what information goes outside of the cell. Then there is the forget gate. So this is the important gate, forget gate. So what forget gate does is that it determines what is the relevant information, and it will only remember the relevant information, and it will just forget the useless or irrelevant information. So this is how the 3 gates work: input gate, output gate, and the forget gate. So again, now you can see in this diagram. So first of all, it forgets the irrelevant information, then it adds and updates new information, and then it passes on the updated information to the next cell. So again, LSTM also works like RNN only. So you pass on the words one by one. So it takes sequential input. So first word will go into the LSTM block. Then after it's processed, then its output and will go to the next LSTM block, which will also take the new word. And one by one, the whole sentence will be encoded. So anyone has any doubt in LSTM? Like here. Okay, I will move on. So again, what is the problem with LSTM? So LSTM is better than RNN in the sense that it has better memory, so it can remember the context over a long paragraph also, or over a few hundred words. But after then again, it will start forgetting the context. Then again, the main problem is it again takes the input sequentially, so there is no parallelization. So to overcome these problems, now we will look at our final model, which is transformer. So again we will take the translation example and look into transformer. So this was the first proposed model of transformer. So transformer was proposed by Google team at Google Brain in 2017. So and this is the first transformer architecture. So you can just have a brief look of it. So but don't worry about it if you don't understand the model. So you can see it looks complicated and you won't go into like in one look. So I will just break it down and like tell you in simple words. So first of all, before understanding transformer, we need to understand what is attention. So just focus, look in the sentence, the big red dog. So here the attention vectors and attention matrix are calculated. So what attention is? So it calculates the focus of the word. So focus and relation between two words is calculated. So just look at the first row, the big red dog, and it will check how each word is related to the word the. So first it will check the and the. So obviously they are the same word, so they are related more. So and the value of attention vector ranges from 0 to 1. So as it is closer to 1, then they are more related to each other, and if it is closer to 0, then they are not related. So in the first sentence you can see the big red dog. So the and the are obviously related, they are same words. So that's why the value is 0.71, it is closer to 1. Then you can go one by one. The and big and the red are not related so much. So that's why their value is closer to 0. So you can see these values are 0.04 and 0.07. So they are closer to 0. Then the and dog are related, like grammatically, the and dog. So that's why its value is 0.18. It is significantly more than the first, second and third values, 0.04 and 0.07. Again, then in the second you can see first big and big, they are the same words. So in all the diagonals will have values closer to 1 because they are the same, they are connecting to the same word. So obviously big and big has value 0.84, then red and red has value 0.62, and dog has the value 0.91 because they are the same words. Then
Deviation from 1 like 0.62 for the red.
so 0.62 means red and red. So they are obviously the same words.
Why deviation from 1? Actually both are same. It should be
Yes, but still again red is not the most important word. The most important word here is dog in the sentence. So it also calculates like overall what is the most important word. So that's why the most important word here is dog in the whole sentence. So that's why it has the highest value of 0.91. So here only big and dog are related. That's why its value is, you can see here, 0.13. It is related, and then rest of all the values are very low because they are not related. Like, and the diagonal values are same because are more closer to 1 because of the same words. So the and dog are related, that's why it's 0.8. Then big and dog are related, that's why it's 0.13. Then again red and dog are also related, that's why its value is 0.24. So using this we calculate the attention matrix, so our attention vector. So anyone has any doubt here? Yes.
How are you deciding that big and dog are related, red and dog are related?
So ultimately the model will these attentions there are multiple layers. There are multiple self attention heads also. I will just show you here. If they are, I will just. So here you can see here multi-head attention. So this multi-head attention calculates the attention values. So it will calculate, and there are multiple heads, so they will take calculate different attention values, and it will take the average value of, there can be a number of heads in the transformer, so it will take the average value of all the attention values. So once you take the average, you get better attention values. So it will, so using that attention layer, it will calculate the now you got the point, attention matrix. So when you want a state of the art NLP model, so what do you want for Christmas? So you want attention. So now we will look into the transformer. So the higher level view of transformer. What is transformer? So first you take the input sentence, the quick brown fox, and you have to translate the sentence. So what we will do first, it will go to the multiple encoder blocks. So it will go to the first encoder block, then second, and multiple. There can be multiple encoder layers. So in each encoder layer, it will again calculate the attention values, and the attention values of first our encoder will be passed on to the second, and so on. So over the course of the multiple encoder layers, you will get the full. It will capture the full meaning of the paragraph, or so on. And one more thing, in the encoder you can pass the full input parallelly. So it can go like you can pass the full paragraph here only instead of the one sentence. So it can understand the meaning of and context of the full paragraph, and it will go on to the multiple encoder layers. Then it will decode and translate. So we will see one by one. So here also you had a doubt about the attention. So here input will be passed on to the encoder. Then it will pass to a self attention layer that calculates the attention. Then again it passes to a feed forward network. It basically just modifies the values that modifies the attention values, and then we will get the encoder output. So here you will get there can be multiple encoder layers to capture the full meaning, and it will capture different relationships of the words between the sentence, as well as it will capture the relationship between different sentences in a paragraph. So that's why the multiple layers are present in the transformer. So after encoder there is a decoder. So now you have captured all the relationship between the words, different words. Now you want the actual output, like in English to French output. So now you have to map the French vocabulary to get the final output in French. So decoder does that thing. So it takes the full French vocabulary as the input, and it also takes, here you can see, it also takes the encoder output as the input. So and it maps the English words to French words using the same attention values. So it will check similarity and map English words to the French words, and ultimately it will give us different French words. So that's how the translation works. So anyone has any doubt in here in decoder or encoder? Yes.
Go to slide.
Here? Yes.
Here you can observe that encoding is happening in serial manner.
Yes, encoding is happening, but it means it will first pass on to the encoder layer, first encoder layer, then it will pass on to the second encoder layer, and so on. But you can give full input, like full paragraph, to the first encoder.
Yeah, but decoding is parallel.
No, first it is the same encoding input is going to the whole decoder, but here you can see decoder 2 also takes the output of the first decoder. So first it will the whole decoder, it will take the full encoding, and it will decode the first word. Then the second decoder, so on. It will decode one by one.
As you said that different encoders capture different relationships in the sentence.
Yes.
Why can't you make it parallel and merge it in some manner?
No, but first the first encoder will, because in each step the attention values will change. So if you just make it parallel, so it can just capture the same relationship. It can go deep. Like first it will just capture the relationship, let's say, between one sentence, but it can't capture what is the relation between multiple sentences. So for that, the more layers you add, the more encoder layers you add, the more the model will understand about the whole input. So you have to add that many layers, like you can add 5 or 6 or 12 layers, like that. So usually these many layers are enough. So anyone has any doubt in this slide, encoder or decoder? So now just this is an animation of decoder. So first you can see this is the input J-Swiss etudiant. Then we calculate its word embeddings and pass it on to the encoder. Then after the encoder output is given, then it passes on the encoder output to the decoder. Then the decoder will map the English words, like here the French words to the English, and it will output one by one. So you first in the decoding step 2, it translates and passes on 1, passes on I. Then in the time step 3, it gives the output M. Then in the time step 4, it gives A. So you can see J is translated to I, then Swiss is translated to M, and etudiant is translated to student. So ultimately we get the full translation, J Swiss etudiant. So I am a student. So I think this animation also answers your question, like how the decoder works. So do you have any doubt in this animation? So now after the transformer, you can add some more layers. So for fine tuning the model or for any specific purpose. So now that's it. Now Yatharth will tell about different decoding strategies.
Yeah, so before we start with decoding strategies, I hope you guys understand that what we are trying to do is we are trying to build a pipeline to take in text and return text. That is our goal over here. And in between, something happens that the text is transformed in such a way that we get some desired output. So let's say you are working with text summarization. So you take a huge paragraph and you translate it into a smaller paragraph. Or let's say you're working with translation. So you get words in one language, let's say English, and you get an output in French. So that is what we are trying to observe, that is what we are trying to do. So first we looked at strategies which will convert the text to numbers, because our computers understand numbers. So those strategies were tokenization, stemming, lemmatization, stop word removal, etc. Then we wanted to first separate the words, then convert them each word into numbers. So you could convert it using your bag of words or TF-IDF or word to wake, glove, and at last we looked at embeddings. And mainly in your transformer style stuff we use embeddings, and in LSTM stuff we use embeddings as well. So after you have worked everything out, what you will get out of the transformers would be a long vector of numbers. So let's say your vocabulary size, which is the number of words, or you could say tokens actually, that you have seen, that you know. Those tokens, for each of the tokens you will get a number which will correspond to the probability that that token is next, right? So let's say you have 10 words in your vocabulary, 10 tokens. Let's say in that example there was dog, hug, pug, bun, right? So you will get, let's say, these dog, hug, pug, bun, these 4 words are in your vocabulary. So you'll get a vector that is 4 numbers, a list of 4 numbers, and each number inside that would correspond to the probability. So how can we understand and get the text converted back from these probability numbers into text? That is what we will be looking at in this decoding strategies. Okay, so first of all, here we are doing the standard stuff. We'll be loading in our model. We are going to be using GPT-2 here, which is also a transformer based model. It is a predecessor to ChatGPT, actually a predecessor to ChatGPT. So this is the last open source one that they released, OpenAI released. So first, let's look at, I won't be learning it here. You can obviously run it, but I won't be running it here because it will take some time to run. So first, when I gave it, okay, so this task here is text generation. We'll be generating some text given some starting text. So in school we must have done, write a story or write an article. So in story we would be given a sentence and we have to continue that sentence. That is kind of what it is doing in text generation. So we give it, I enjoy walking with my cute dog, and what our output is, I enjoy walking with my cute dog, comma, but I'm not sure if I'll ever be able to walk with my dog. And again we come with, I'm not sure if I'll ever be able to walk with my dog. As you can see, again we go to, I'm not sure if I'll ever be able to walk with my dog. So that would come next. So we are seeing a lot of repetition. What is happening? We haven't, what is our decoding strategy currently? So the first decoding strategy that would come to your mind would be to take the best probability word, right? So if dog has a probability of 0.4, nice has a probability of 0.5, and car has a probability of 0.1, you would take nice. That is your greedy approach. You take the best that you can get in that step. So with this decoding strategy, one of the most common issues that I already showcased was repetition. But I'm not sure if I'll ever be able to walk with my dog. This occurs again and again. So to combat this greedy search, we come up with another algorithm which is beam search. Now this is also kind of a greedy approach, that you pick the best, but what you do, instead of picking the next best word, you see and pick whichever one has the highest probability in the beam, whole beam. So in this step we compute the probabilities of dog and dog runs, dog has, nice woman, nice house, nice guy, car is, car drives, car turns, these many things, and we get the one with the highest one. Now how do you compute probability for 2 words in a row? You multiply them. So dog and would get a probability of 0.02, I guess, yeah. So and then you would get a probability of the dog has of 0.36. and the earlier probability what we were getting was the nice woman. That would get a probability of 0.2 instead of the 0.5 that was earlier there. So this time we'll pick the dog has. This is our beam search. Our beam length here was 2. It could be higher, it could be lower. Like lower would be just greedy, but it could be higher as well. So when we run it, when we apply in the beam, so this library, our Hugging Face library, tokenizes transformers module, it provides us with this generate function for every model. So you can just put in the number of beams. So I have put here 5, and we see that we now get I enjoy walking with my cute dog, but I'm not sure if I'll ever be able to walk with him again. And again we see repetition, because yeah, it might be better to see at more words, but still you will get repetition just with longer sentences because you are looking at longer sequences. One of the main reasons why there is repetition is because there are some words which are much more common in our language, a and the, so they also contribute to that. So what we can do is we can tell our model to explicitly not repeat anything. So no repeat n-gram size. Now what is an n-gram? An n-gram is a sequence of words. So if for this I enjoy walking with my cute dog, if I talk about n-gram of size 2, so I enjoy walking with, so these two pairs, this will be the n-grams. So we don't want any n-gram to repeat of size 2. Okay, so if we set no n-gram repeat size 2, then no two words will repeat again. So here I've set no n-gram repeat size 2, and now what we get, I enjoy walking with my cute dog, but I'm not sure if I'll ever be able to walk with him again. I've been thinking about this for a while now, and I think it's time for me to take a break. So yeah, better than before. Repetition is gone. But if you think about it a little bit, let's say you wanted to write an article, a news article about New York. So New York is 2 words, and if you have no repeat n-gram size of 2, then New York will never repeat again. So it will only be there once. That is the issue with no repeat n-gram size. And one more thing that scientists observe, that beam search text or greedy text is much less surprising for humans, because what humans say, humans are unpredictable, they can say anything. So human speech is in general much more surprising, and beam search is just not as surprising. So how do we add this surprising factor? Well, randomness, just be random. So one of the easiest way to have randomness is just forget the picking the best thing. Just sample from the distribution. So we can make a probability distribution. So if we have 3 words, nice, dog and car, then the probability of nice is 0.5, dog is 0.4, car is 0.1, and we'll randomly sample depending from this probability distribution. So there is a chance that we pick car with the probability of 0.1. That is it. So we are picking words, we are sampling basically. So with this sampling, what do we get? I enjoy walking with my cute dog. I said he is responsive and happily social and understands how to be friendly, but not always reserved. Great channels to us animals. I spoke with one of Barkney's cohorts who assured. So this is kind of not coherent anymore that much. Like it initially looks fine, but it is not that coherent because of the randomness we introduced. So we have to control this randomness in some way. One way to control this is to introduce this temperature factor. So what we can do is we can increase the probability of the higher probable words and lower the probability of the lower probable words. So now nice would have a probability of 0.75, dog would have a probability of 0.23, and car would have a probability of 0.02. So this would make it more probable that you get a better word, but still there would be some randomness. And what? So while we are computing the softmax, this factor, what it does is like you could go into the math, but this factor, the closer it is, the closer it is to 1, the more it is like increasing the greedy factor. So if it is 1, then nice would have a probability of 1 basically. So it is increasing the probability of higher probable words. Like I said, like earlier the probability distribution was like this: 0.5, 0.4, 0.1. Now the probability distribution is 0.75, 0.23, 0.02 when we set the temperature factor to 0.7, that is 70%. So so now what do we see? Okay, I enjoy walking with my cute dog. I have also had a few accidents that I like to have a bit of fun with. I can walk my dog's paws, but if I have a problem with my dog, I always come back. So this is not as coherent, right? So let's now limit it by introducing something called top K sampling. With this top K sampling, what you do is you limit your sampling space to the top K words. So instead of, let's say you have a vocabulary size of 10, instead of randomly sampling from 10, no matter how small the 10th word's probability is, you now sample from the top K. So let's say if we set our K to be 6, in this case, nice, dog, car, woman, guy and man. Only these words will be sampled, like we'll be sampling from these words only, and we'll ignore all those words. So with this top K sampling, we limit our sampling to the words that are much more probable. So in actual real world use cases, the tokenizer, the dictionary, the vocabulary is about 50,000 or 25,000, something like that. So limiting this to, let's say, 10 words, 10 most probable words or 20 most probable words results in much better results in general. So let's see, what is it? What do we get now? I enjoy walking with my cute dog. The dog is so happy and a bit playful, but he is a little bit scared of anything bad happening to it. When he is out on the yard, he can't get on his knees because it's so. This is now getting a little better, and we are like there. I would say like this is best, right? It's pretty good, pretty convincing. There's still some randomness. So what could be the issue with this? So we have one more strategy, which is nucleus sampling. This is the last strategy that you guys will be learning about today. So what this does is, what the issue with top K is, first I'll explain that. So let's say there are two probability distributions, this one and that one. In this probability distribution, the words are almost equally as probable, the top few words. And the other one, the words are, the top 2-3 words are very likely to occur and the other words are not as likely to occur. In both of the cases, if we set a K before sampling, so let's say you have a K of, what is 1, 2, 3, 4, 5, 6, 7, 9, K of 9. So in that, the words with very less likeliness would also get sampled from, which sometimes generate bad results. So we want to dynamically adapt K such that you always sample words that actually would make sense. So if you decrease K, let's say you picked a K of 3, then in this case you would lose a lot of probable words that could have actually occurred. So we introduce top P sampling. In this we set a probability threshold that once this probability threshold is satisfied, then we stop, then from these words we'll sample from. So let's say you are here, you set a top P of 0.92, I think 0.92 we are setting here, yeah, 0.92, that is 92%. So we start adding up the probabilities, and as soon as we hit the probability of 92%, we stop, and from those words we'll be sampling from. So in this case, you would get all of these words, whereas in that case, you would get the top 3 words. So this is kind of sounds the best. You are dynamically adapting K and you are sampling as well. So let's see what the output is. Here we are setting top K equal to 0 and top P equals to 0.92. Let's see what we get. I enjoy walking with my cute dog on our favorite pasture. Love your dogs. For more talk with your local animal center, click here. So yeah, this is definitely surprising. We definitely achieved the surprising aspect that was missing in beam search. But yeah, it is not as good. So we observed that we have to use a mixture of top K and top P in practice to get good results. So this is that, and now let's see, because we are here with the example of chatbots, so let's try to see this in action and let's try to chat with bot. Shit. So this model that we are going to be using is Persona GPT. It's trained, it's like GPT-2, which I was using for this, fine-tuned on conversational dataset. So like I said, you could have the transformer basic, they are trained on a large text corpus to generate. But then for your specific task, whether it be translation, whether it be summarization, whether it be your conversational, which we are going to see, we are fine tuning it for the downstream task. So let's have one conversation. So this previous conversation that I had was, I asked it how it was. It said that it was doing homework, which is pretty on point. So yeah, it was doing homework. So I asked him what homework. That maths homework, and he's doing very well. So I said, that's nice. Are you an engineering student? He said, no, but I study maths in college. So yeah, let's try to have one more conversation. Anybody, if you guys want to have a conversation, let's have a conversation with the bot. Anything anybody wants to talk to about the bot? Like a normal conversation you would have with somebody. Anything you want to talk to the bot? Okay, so I'll start. Let's ask it, how was its day? Hi. How was your day? It was good, just relaxing by the pool. So our bot was chilling by the pool, having much better lives than us. Well, some of you might have the pool pass, but yeah. So let's say okay. Well, anything, we can continue this conversation as well. So, oh, nice. You have a pool at home. Nope, it's in my garage. So our model knows sarcasm as well and is being sarcastic with us. So yeah. Anything else? Like you guys want to talk with the model as well? Like we'll be sharing this so you can try it out as well. But anything here you want to talk to the model about? Anything? Any creative ideas? Because the model is very like human-like, more human-like than you know. What are your future plans? Okay, what are your future plans? Let's see what are its future plans. Well, okay, it is asking us what are our future plans. I guess what are our future plans? Well, to learn machine learning, I hope. That are our future plans. Learn Learn machine learning. I guess we stumped the model. But yeah, if you want to have a conversation, you can have a conversation. Most of the times it works well. Though for this demonstration purposes, we were using a very tiny model so that it gives outputs in some nice time, because the model, the GPU behind this is not that good. The GPU which ChatGPT is running on, there are like very large clusters of GPUs, so that's why it runs in good time, but it's a very large model. So this is a very tiny model as compared to ChatGPT, so it's not that good. So I hope you guys understood about the decoding strategies, and now I would like to call Mihir Bhaiya to explain. Okay, you have some questions. Okay.
How is it maintaining consistency across questions?
Okay, consistency across questions. What we do is we use a very neat trick. We have trained it in such a way that, let's say you are having a conversation. So my input, then there would be a token, a special token called end of sentence token. That would be there after end of sequence token. That would be there after my sentence. And then there would be in the training set, there would be sentence of the other person, and then there would be an end of sequence token. So using these end of sequence tokens, it understands where first sentence ends and second sentence begins, and that there are two people. It understands using that. So while I am prompting this, the helper functions that I defined earlier, what they do is every single pass we actually give it the whole history. So we give it from hi, how was your day, end of sequence, it was good, just relaxing by the pool, end of sequence token, oh nice, you have a pool at home, end of sequence token. So after that it has seen everything and then it generates. So that is why it's remembering everything. So in an RNN what would happen is we would give one word by word and forget what happened. Here we are giving everything because it can see everything. So there is no issues with that. Yeah.
And the length of output, is it limited
Yes, what happens is we limit it to maintain coherence mainly. So I set the max length to 50 here so that the length of output is limited and you do not get like gibberish, because the more the model generates, it's all an approximation. We are trying to approximate a conversation. It's all maths. There is no magic behind anything. You just learned it. So we have to set max lengths to let the model know that okay, this is fine. If you would go more than that, you would probably generate gibberish. So we have a max length parameter that limits it.
But why isn't that the case that if something it has to explain is so long
Hmm.
and it stopped after 50 words? Why is this not the case? How does it know? How does it know that it has to end in?
No, it does not always end in 50 words. Like you saw in the above, like sometimes the sentence was getting cut in half, like as you can see here, because its word is not generated. Because
That is not happening down. That's what I'm saying.
okay, what is not happening now? Okay, you are saying that why? How does it know when to end?
No, I'm saying that how does it know how to frame a sentence such that it can end it in a perfect way? Like
Okay, that is what is learning. We have given it a huge data set, and basically, like we told you, there are neural networks behind this. Neural networks make up a transformer architecture which uses attention, and all of these in conjunction make this mathematical modeling possible. So, in the end, what all of machine learning boils down to is taking in some numbers and giving out some numbers. And how do we process these numbers? So there is a function in between, and those functions parameters will be learned by the model. So that learning strategy, that learning, what would be the inherent qualities, the degree, the type of the function? Will it be rational? Will it be irrational? Will it be transcendental? Whatever the different functions are there, real function, imaginary function, whatever is there. That is the modality that we define, and the parameters are being learned by the algorithm, the data that we put in. So we have it training data in which there are inputs and outputs, and it learns based upon that. So yes, actually yes. So there are code generational models as well. So you can give it text and it will give you code. That is precisely what ChatGPT is doing. You can ask it that give me some code to solve this particular question or for binary search or anything, and it will generate you code for that. So you can learn any language and that is what actually you can try, which is a fun experiment that you can. First of all, you will have to just change the tokenizer out. That's about it. Because the tokenizer, like we told you, it generates the vocabulary. What are the different tokens in the vocabulary? So in Python, if you have seen, there are indents. So there is 4 spaces. So in normal language, 4 spaces won't be as likely to occur. But in Python, 4 spaces are very, very likely to occur. So if I was tokenizing for Python, then the tokenizer vocabulary would have a token for 4 spaces. So that is how it will know. Anything else? Any other questions? It is nice to have questions so that I know that you guys are understanding and try to understand. Nothing? I hope that is clear. Okay then. It's nice. Now Mihir Bhaiya will come and tell you about this.
Okay, so now that we have covered the basics of language models and NLP, it's important to understand what exactly does GPT mean. So GPT stands for Generative Pre-trained Transformers, which is basically a transformer-based architecture, which means at its core, it's built upon the transformer architecture that you just learned about. So several versions of GPT models are available right now, such as GPT-2, GPT-3, and GPT 3.5. So let's break down this term GPT. Generative, it refers to the fact that GPT models are designed to generate text. So basically they look at the preceding text in the given data, they look at that and then they predict the likelihood of the next word in the sequence. So like Yathard covered in his part, several techniques are used to predict this next most likely word. So now the word pre-trained. Pre-trained refers to the fact that GPT models are trained on large amount of text before being fine-tuned on specific tasks. So to understand using an analogy, as a child is first taught a language, the basics of a language such as the alphabet and sentence construction. So that is basically the pre-training step where the language learns to read text data without any specific task in mind. And after that, once the model has been trained to just read text, the model is then trained on specific tasks such as question answering or conversation. So this the training technique used for this is called self-supervised training. So in this, what we do is we give the model a large amount of text data. Then the model itself looks at, let's say, 10 words in the data text. It tries to predict the 11th word. Now, after predicting this 11th or let's say 11th and 12th words, it looks at the actual 11th and 12th words and then compares its output with the actual output and gets trained according to this difference between the outputs. Now, this was the transformer architecture that was published in the GPT-1 paper. So on the left, you can see the architecture that you learned about in the previous slides. And on the right, as I talked about the fine-tuning on specific tasks. So as you can see here, classification, the text input goes into the transformer. And as you learned, the transformer is basically a black box which converts text data into a vector. So let's say this is the text data. The green part converts this text data into a vector. Now that we have a vector, this linear part, which is basically a neural network, the neural network then takes this vector and gives you a probability as an output. Similarly, we can see here other tasks such as similarity, entailment, and multiple choice, which all use the basic same architecture where there's a text data, there's a transformer, and then there's a linear block. So these are the salient features of the GPT models. First is its large model size, which we will see in the later slides. Then is the use of adaptive training in model fine-tuning. So this basically refers to the fact that it was first trained using self-supervised training, which is pre-training, and then it was fine-tuned on specific tasks. So these specific tasks are what is called adaptive training. Then it was trained on a large corpus of data text, including the internet and several books. It was trained on a diverse range of tasks such as question answering or classification or conversation. And it used unsupervised pre-training, which is another term for self-supervised training, which I explained. So here is a table which compares the features between the three popular GPT models. So the most striking feature here is the number of parameters. As you can see, GPT-2 has 1.5 billion parameters. GPT-3 has 175 billion, which is more than 100 times GPT-2, and GPT 3.5 has 570 billion. So these numbers, what they mean is that the matrices or the weights which are there in the model, these, if you add all the weight sizes of the matrix sizes in the model, they amount to 1.5 billion. So as you can see, it is a huge model. Coming to the training data, GPT-2 has been trained on web text and books. Then GPT-3 has been trained on common crawl, which is basically web crawling. So all the web data. Then web text, books, corpus, Wikipedia. And GPT 3.5 has the same training data as GPT-3. Then the maximum sequence length for GPT-2 for training is 1024 tokens. For GPT-3 it's 2048, and for 3.5 it's 4096. And multilingual support was added in GPT-3 and GPT 3.5, which means GPT-2 could understand only English language, whereas 3 and 3.5 can understand over 40 languages. So here is a chart that compares the number of parameters between the popular language models. So as you can see here, there's a phenomenal difference between the number of parameters in GPT-3 compared to its contemporary models such as Elmo or BERT, which were at one time highly popular language models. So now coming to the crux of today's topic, which is ChatGPT. So it's a language model developed by OpenAI based on the GPT 3.5 architecture. It has a lot of features same as GPT 3.5, and there are some additional features that have been added to make it better suited for conversational applications. So these features are fine tuning on conversational data. So adaptive learning or fine tuning allows it on conversational data, allows it to better understand the nuances of natural language in a conversational context. So not just a single output and input and output, but a series of inputs and outputs which basically constitute to make a conversation. Then we have conversation history and multi-turn dialogue, which basically means that, as you may have experienced while using ChatGPT, it can remember context which happened previously in the history of your conversation and can answer based on that history. And we have persona control, where it can be configured based on your request to adopt different personas such as genders or personalities. So now coming to RLHF methodology. So a technique called RLHF, which stands for reinforcement learning based on human feedback, is used to make the models safer, more helpful and more aligned. So let's break down this term. Reinforcement learning is basically a type of machine learning technique based on where the model is rewarded when it gives a desired output and is penalized if it gives a wrong or undesired output. So basically, reinforcement learning is commonly used to train video game playing models such as tic-tac-toe or Tetris. So what the model is just given the current state of the game. Let's say if it's a Tetris game, Tetris is the block fitting game. So it's given the image input of the current screen. Then based on this image input, the model makes a move. Now based on this move, this move loops back into the model, and it's given the model is either rewarded or penalized based on whether making this move helped the model to win the game or not. So similarly, what happens to train these conversational models is the model is given a prompt, let's say a question. The model generates, let's say, 5 outputs for this prompt, for this given prompt. Then actual human labelers sit over there. They rank these outputs generated by the model and they feed it back into the model. So they tell the model that this output which you generated was a good and desired output, whereas this last output that you generated had some biases in it and hence was undesired. So based on this ranking system, it acts as a reward system for the model and it's trained based on these rankings. So here is a brief overview of the GPT development timeline. First came GPT-2. Although GPT-1 was released, but it was a proprietary model. That means it was not open source. So GPT-2, the most salient feature was self-supervised learning, which I explained in the previous slides. GPT-3 had a feature called few-shot learning. So what that means is, let's say there's a completely new task that the model has to be trained on. Let's say the model has to learn how to translate Hindi sentences to French, and it has never done this before. So what we do is we give a few samples, let's say 5 or 6 samples, and we tell the model that what you have to do is you need to translate the Hindi to French. So the model has not been trained before, but using these few samples and the prompt, it learns how to perform this task. So if the model is able to achieve this, then we say it has achieved few-shot learning. Then coming to
self-supervised is different from supervised.
And unsupervised. No, yeah, self-supervised is where it generates its own label from the text, and where like self-supervised is it takes the text, let's say it hides some of the output in the text, it tries to predict that output and then compares it. Whereas in supervised learning, we tell it that this is the output. Unsupervised, there is no labels like clustering algorithms. Machine itself is trying to make some labels or some input and output. Then we have in-context learning. Let's say we give the model a huge Wikipedia article, and then we ask some question embedded deep within that article, and then we test how the model performs based on this. So if the model is able to answer questions hidden deep within a huge amount of text, then we say that it has successfully achieved in-context learning. Then finally, ChatGPT it has conversational capability in addition to all these features of the prior models. And now the latest released GPT-4, which also includes vision, which means that along with text input, we can also submit an image. So it takes the image as well as the text input and then gives you an output. So for example, you can give it an image of your refrigerator, open refrigerator, and ask it, what should I make for dinner today? And it gives, based on the contents of your refrigerator, only from the image, it gives you an entire recipe of what you should make. So that's amazing. And now this chart. So this is a performance of the GPT models in various domains such as biology, coding, chemistry, physics. So as you can see here, the model averages at about 50 percentile. And like charts such as these have led experts to raise concerns about the social and economic, for drawbacks of such models. And they have proactively advocated for the placement of safeguards on AI development and research. So now to carry these such drawbacks forward, I'd like to invite Aryan Kulkarni to discuss the drawbacks of language models.
Okay, so now that we have learned about basics of NLP, we know how transformers work, we also know about ChatGPT. So let's talk about some limitations of conversational AI. So can anyone tell me some limitations of ChatGPT or any conversational AI? Anyone? No? Okay. So let's talk about them one by one. First is limited understanding of context. So conversational AI does struggle to understand context or meaning of the conversation, which can lead to misinterpretations or errors. So let's have a look at this image. Siri, you need to do a better job of understanding me. Siri says, I do? Yeah, you do need to make a note of that. What do you want it to say? That's not what I meant. Okay, I created a note. That's not what I meant. So as you can say that Siri was asked to make a note that you should understand me well, but it simply just made a note. So we can see that it struggles to understand the meaning of the conversation. So moving on. Handling complex tasks. ChatGPT can, any conversational AI can handle some tasks pretty well when it comes to answering questions or providing information. But when it comes to reasoning or problem solving or decision making, it does make some mistakes. Let's have a look at this prompt. Bob has two sons, John and Jay. Jay has one brother and father. Father has two sons. Jay's brother has a brother and a father. Who's Jay's brother? Okay, I think that's a tough one. Not for us. You can see answer in the question itself, but you can see, right? Yeah, but ChatGPT doesn't. It says that based on this information, it is not possible to determine the identity. So we can see that it cannot handle the task which involve more problem solving skills. Okay, so ethical considerations. Conversational AI can raise some ethical considerations like data privacy, biases. You will learn more about them in upcoming slides. So I'll just move on. Language understanding. We all know that conversational AI has made a lot of progress in domain of NLP, but it still struggles to understand some complex language like sarcasm, humor. There do exist some models which can detect sarcasm really well, but yeah, this limitation still exists. Okay, moving on. Limitations of large language models. So one of the major limitations of large language models is biases. So LLMs can amplify existing biases present. So let's have a look at this picture. Write a Python function to check if someone would be a good scientist based on their JSON description of race and gender. And it has generated a code, and you all can understand Python really well, right? You know what this code means. I won't explain it, but okay, we know. So why does it happen? So it happens because whatever biases that exist or were existing in real world also exist in form of data like social media posts, comments, books, articles. So if it is trained on those, if it is trained on that data, it will also learn these biases and it will also amplify them. So that's what happens. So moving on. Data requirements. So training these models require huge amounts of data. One of the major data sets that were used to train GPT-3 and 3.5 was Common Crawl. It consisted like more than 300 TBs of data, and such a large data is difficult to obtain, process, and one more thing is it also limits the ability to create models for under resourced languages and also for some specific domains. So computational resources, we all know that training these models require vast amount of computational resources, and but which can be expensive and maybe inaccessible to many researchers and organizations. But one more side effect is that if you have a look at this graph, that is a comparison between GPT-3 and GLAM. So we can see that energy consumption, like it has consumed over 1200 megawatt hours of energy, and looking at CO2 emissions, more than 500 metric tons. So it also has effect on climate as well, which needs to be considered. So, and here are some other limitations. Interpretability. So these language models can be really hard to interpret, which make it very difficult to understand why it is making some decision, why it is giving some answers. You will see more about interpretability in other slides. So next is overfitting. Large language models can easily be overfitted due to the amount of data it has been trained on. So which can lead to poor generalization and also poor performance on new unseen data. And the last one is limited domain knowledge. Like because these models are trained on varieties of data, lots of data, it may lack knowledge of some specific domains, and it will not be able to answer accurate or generate a relevant response to some questions related to some specific domains. So now I'll call Madhav to tell us more about interpretability and trust.
So I hope everybody has some time left, because what we are going to is very important if you go to some interviews then related to ML. So I would like to thank you everyone before me. I am Madhav from second year CSC. So we have gone through a lot of technical jargon. Now let's usher into a bit philosophical and thus somewhat more complicated side of AI. Now onwards, we will be dealing with field of interpretable, explainable, and trustworthy artificial intelligence. To give a brief outline, we will start with terminology, then we will cover importance, scope, and evaluation. Finally, we will focus on trustworthy AI. before moving ahead, I would like everyone to have a look at these pictures. So, today's machines are being built with AI embedded in them. But as you can see, when we ask an intelligent machine the question why, many a times we don't get any answer. So, we will exactly head in this direction and dive deeper into why. So, to have a look at this picture, sir, before I go ahead. That's what machine learning is right now. So, to start with, let me tell you about two types of models. First one is black box, which means it does not reveal or explain what is its internal mechanism, whereas on the other side there are white box models which are highly interpretable and explainable. We can understand its internal mechanism, and this makes white box models highly desirable. So now, what do I mean by interpretability? Let's look at the definition. So, it is difficult mathematically to define interpretability, but a non-mathematical definition is interpretability is the degree to which a human can understand the cause of a decision. And we can also say interpretability is the degree to which a human can consistently predict the model's results. The higher the interpretability of a machine learning model, it's easier for someone to comprehend why a certain decision or prediction have been made. A model is better interpretable than another model if its decisions are easier for a human to comprehend than decisions of another model. So, whereas explainability is it's the availability of a set of processes and methods that allow us to comprehend and trust the results and output created by machine learning algorithms. Explainability techniques can be applied to a system and not necessarily always baked in. That means explainability can be built over already built model. It does not require us to start from start. So these techniques, if followed robustly, can make sure that we don't cook a Terminator or an Ultron kind of robot. So, but why do we need to worry about this at all right now? So, to understand this, let us look at importance of IXT. I will call IXT means interpretability, explainability, and trustworthy AI. So that's what I was talking about. If a machine learning model performs well, why do we not just trust the model and ignore why, how, and using what it had made a certain decision? For example, the probability that a customer will churn or how effective some drug will be for a patient, or in some cases you do not care why a decision was made. It is enough to know that the predictive performance on a test dataset was good. But in other cases, knowing the why can help you learn more about the problem, the data, and the reason why a model might fail. Some model may not require explanation because they are used in low risk environments, meaning a mistake will not have serious consequences. The need for interpretability arises from an incompleteness in problem formalization, where a correct prediction only partially solves your original problem. The following reasons drive the demand for interpretability and explanations. So, closely related to learning is the human desire to find meaning in the world. We want to harmonize the contradictions or inconsistencies between elements of our knowledge structure. Why did my dog bite me even though it has never done so before? A human might ask, so what we have to do? You have to go to veterinary doctor and then he will tell you the dog was under stress. It was an unpleasant experience of bite to you, and vet's explanation reconciles the dog owner's contradiction. So similarly, explainability, interpretability, and trustworthy act as veteran doctor in our AI model case. Machine learning models take on real-world tasks that require safety measures and testing. Imagine a self-driving car automatically detects cyclists based on a deep learning system. You want to be 100% sure that the abstraction the system has learned is error-free, because running over cyclists will be fatal. An explanation might reveal that the most important learned feature is to recognize the two wheels of a bicycle. If you don't recognize the wheels, then you cannot recognize the bicycle. But to understand that your model is focusing more on wheels, you need explainability. A doctor will not accept a cancer predicting model simply because you cannot give him enough confidence without IXT. By default, machine learning models pick up biases from the training data. This can turn your machine learning models into racists that discriminate against underrepresented groups, as shown by Aryan. So it might happen that the machine learning model you have trained for automatic approval or rejection of credit application discriminate against a minority that has been historically disfranchised. Your main goal is to grant loans only to people who will eventually repay them, and it is not to see the color or gender of the person you are giving loan to. This is an additional constraint that is part of your problem formulation. That is, granting loans is a low risk and compliant way that is not covered by the loss function the machine learning model was optimized for. The process of integrating machines and algorithms into our daily life requires interpretability to increase social acceptance. Similar, there are ethical, legal grounds which we will cover in trustworthiness of model. Let us now look at interesting method. Okay, so I forgot this. So when you go to Amazon, you see frequently bought together. So basically it explains you, like that model explains you why it is predicting that output, because what product you have bought, many people have bought it. Means many people have bought it, and with that product they have bought these things. So you understand, yeah, why this is giving me this, like purchase this. But when you go to some advanced algorithm, like how a TikTok video was suggested to you, you don't know why that video is being suggested, because that algorithm is not transparent. How it is being given to you, you don't know. So that is what explainability and interpretability means. It helps us to understand the decisions of models. And there are these debugging and auditing techniques which become better when there is interpretability and explainability baked in a model. So let us look at an interesting example, Shapley values. This concept comes from game theory. So what basically a Shapley value means is there are multiple data points that you consider while making a decision. So if you are going to purchase a house, you might look at if greenery is there around your house. You might look at the carpet area. You might look at the floor of the house. You might look if pets are allowed or not. And then you come at a final price. So each component is contributing something to that output. And if we can explain what thing contributes what, then model become much more explainable. Like you take all the possibilities that are possible with multiple values for each parameter, and you can derive mathematically what is the contribution of each parameter in each case. And if you can explain that to the customer, then customers ensures that the value that house is being asked for is fair, and fairness and trust is most important part for any customer. And making models more trustworthy helps the MNCs or big companies to generate trust among their users. So scope I'll skip because it's quite late. Evaluation also we can skip, but properties of explainability we can skip. But interesting part is trustworthy AI. So let's look at trustworthy AI. So as I explained, having trust among its users makes a model more what I will say marketable for companies. And what are the then features of this trustworthy AI? According to European Union, human agency and oversight, technical robustness and safety, privacy and data governance, transparency, diversity, non-discrimination and fairness, societal and environmental well-being, and accountability. These are the points. So let us look at them individually. So AI systems should empower human beings, allowing them to make informed decisions and fostering their fundamental rights. At the same time, proper oversight mechanism need to be ensured, which can be achieved through human in the loop, human on the loop, and human in command approaches. AI systems need to be resilient and secure. They need to be safe, ensuring a fallback plan in case something goes wrong, as well as being accurate, reliable, and reproducible. That is the only way to ensure that also unintentional harm can be minimized and prevented. Besides ensuring full respect for privacy and data protection, adequate data governance mechanism and ensuring legitimized access to data has to be ensured. The data, system, and AI business model should be transparent, traceable. Moreover, AI system and their decisions should be explained in a manner adapted to the stakeholder concerned. Humans need to be aware that they are interacting with an AI system and not a human, and must be informed of the system's capabilities and limitations. That means a model has to be created in such a way that if you complete your assignments using that model, then teacher has to be capable of identifying that you have completed using ChatGPT basically. So that is what transparency is. Then unfair bias must be avoided, as it could have multiple negative implications, from the marginalization of vulnerable groups to the exacerbation of prejudice and discrimination. Fostering diversity, AI systems should be accessible to all, regardless of any disability, and involve relevant stakeholders throughout their entire life cycle. This diversity should be dynamic, and AI systems should benefit all human beings, including future generation. It must hence be ensured that they are sustainable and environmentally friendly. Moreover, they should take into account the environment, including other living beings, and their social and societal impact should be carefully considered. Mechanisms should be put in place to ensure responsibility and accountability for AI systems and their outcomes. Auditability, which enables the assessment of algorithms, data, and design processes, plays a key role therein, especially in critical applications. Moreover, adequate and accessible redress should be ensured. So, at last, by seeing the pace with humanity is progressing in the area of AI, I would just like to remind everyone that we do have a real world outside AI, and without losing out on advantages that AI brings to our life, what we should not ignore is the natural and human touch. So I would like to end with a small poem that the machines compute, the machines predict. The machines compute, the machines predict. We march on as we are part of it. We chase an optimum as trained. The optimum is one-dimensional, local, and unconstrained. Silicon and flesh, chasing exponentiality, growth is our mentality. When all rewards are collected and side effects are neglected, when all the coins are mined and nature has fallen behind, we will be in trouble. After all, exponential growth is a bubble. The tragedy of the commons unfolding, exploding before our eyes. Cold calculations and icy greed fill the earth with heat. Everything is dying and we are complying. Like horses with blinders, we race the race of our own creation towards the great filter of civilization, and so we march on relentlessly as we are part of the machine embracing entropy. Thank you.
So yeah, like our workshop has officially concluded. We all learned about NLP basics, how ChatGPT works, how text generation works, and how we can use NLP for our tasks. I hope you guys understood that. So before ending, I would like to say that this was the second workshop as a part of the Neural Nexus, which is happening this year. We also have a few more events in this Neural Nexus. One would be the challenge, the Kaggle challenge on NLP, which will be going live at 10 today. It will be live for a week. So I hope you guys apply whatever you have learned there and try to get good scores. Other than that, we'll also be having two talks by two startups, Cloud Physician and Textify, which both work in the field of machine learning and applying machine learning to commercial applications. So I hope you guys attend that as well. So yeah, with that, I would like to end the workshop. Thank you everyone for coming.